Good morning, everybody. My name is Joey White-Swift.
I'm William Pasha.
Miguel Solis.
And I'm Robert Heeman.
And this is EVOTS. So we set out to come to Senior Design 2 and cook food. And we're happy to say that we are going to be successful in that. So the first semester, we did a lot of research and development. There's a lot of work that we had to do to determine the right types of coils, the right types of power supplies. And then once we had that going, at the end of Senior Design 1, we had sort of just one sort of small module that sort of just turned on and could heat. But over the summer, we have actually integrated a full I2C bus that connects each of the individual modules together. They're each controlled by an Arduino with a Raspberry Pi on the back end as sort of the master control surface. Each of these then has a temperature sensor that can determine what the temperature of the surface is in order both to provide safety as well as to determine when to turn on the light. So that way you can have a safe sort of surface. And again, the intent of this surface is to replace the normal stovetop. So you can do food prep right next to the actual space where you're going to be doing your cooking. Then along with this, we also have both blue and red LEDs. We have a blue cold exclusion zone that allows you to go in and turn off the coils underneath. Because if you're using your phone to look at a recipe, you really don't want to set it down and fry it, right? Or you also don't want to be stirring something and set it down either and have it start heating up. Then we also have the actual ZVS power supply in the coil. And from the back end, we just have a strong power supply. It's actually running everything. So in our testing, we have been able to turn on different coils across the surface. For our prototype, we did a 3x3 surface. And we were able to have pans of multiple sizes. And because we use very small coils, you can actually turn on multiple areas on the surface and put down a larger pan to get more even heating. Along with that, we were able to reach over 105 degrees Celsius in our testing. We used a laser thermometer to confirm this. And so we've been able to cook food, as Dr. Skinner related to in the past, as well as we have a number of safety input functions. And so that way, if it's a blue exclusion zone, you can't override that and turn on the space.
What difference is that from the regular graphite, the ones that you have right now that basically are burnerless that you just turn on and turn off?
So when we were looking at sort of the need case for this, we were looking to see what would be really useful for like restaurants or maybe even sort of small case. And what we found was that with the larger burners, you can put down a pan and if you have a very large pan, you don't get necessarily as even of heating. Whereas with a bunch of very small coils, you're able to get much more even heating across the surface. Additionally, the way that we built it with using the ZVS power supply approach, we were able to get significantly less power use for the same amount of heat. But effectively, how it works with like a cast iron pan or something like that, it's the same principles.
So how fast does your residual heat dissipate?
So the surface that we ended up going with was a concrete board surface, and we found that within a minute to 2 minutes, it's safe to the touch. It may still be warm, but you're not going to get the sort of third-degree burns that you would get with a traditional electric stove.
But your maximum temperature is only 105 degrees Celsius. Like, doesn't a typical stove get much hotter than that?
I'm going to turn this over to you.
It is possible, but when you took a realistic approach, when you are boiling a pot of water, because that's normally the highest temperature you go for cooking on a stovetop, for boiling water, it's 100 Celsius. When you get past that point, do you ever keep it at that temperature, or do you turn it down because the water starts getting too high and the food's already cooking?
Well, I mean, typically you might want to cook a steak or something else that requires you to brown, or you might be using something with oil if you're frying something, and then those applications typically you'll have much higher than 105, than 100 degrees.
I have not looked into the temperatures for specific cooking types, so I did not know that, and that is a very interesting point to make.
In our testing, we were able to easily melt butter and brown bread to make toast. So we can get to the heat, and we can get sort of a sizzling effect from it. So we felt that that was an effective heating. Yes, sir.
I have a question about the efficiency. How is it even defined in a stove? I mean, you want heat, so
So-
where is power loss? Where is it energy
So
lost?
we looked at average temperature or average powers consumed by normal stovetops, and an average stove runs at about 1,200 watts for just turning it on, running it, and ours runs at about 120 watts per coil.
Achieving the same cooking results?
Yes, sir.
Okay.
Now, I would like to point out that although our coils are a smaller size than maybe the traditional, the overall heating is still the same with less power throughput.
So how many coils do you have in your testing bed?
We have 9 coils.
9 coils.
Yes, sir.
Yes, sir.
It's a 3x3 set of coils.
Okay.
What are the additional safety features you have mentioned in the slide?
Robert did a lot of the coding, and I'll pass some of that over to him.
A lot of the safety involves temperature sensor and limits on the temperature sensor and the coil turning off when you hit max temperature. We also have this blue zone, the blue exclusion zone, so that way it doesn't heat anything accidentally.
From a hardware perspective, when each of the modules are sort of set up and instantiated through the I2C network, we actually take and put a maximum safe temperature in them on runtime. So that way, even if they lose connection to the Raspberry Pi over the network, they still know that, again, in a failure situation, when to cut themselves off. We also have, we did look at, although we didn't integrate it into our prototype, a physical switch, just because the amount of amps that we were drawing was larger than most of the switches that we could find easily. But since the power supply that we're using has a lot of built-in safety functions, we're sort of deriving some of our safety from that as well.
Let's thank the team.